Good evening. I want to give a shout out to Mrs. Manton for many of the problems in these notes, as well as problems that we've done previously. Thank you. Your notes are fantastic. I want to start with analysis of set theory. Set theory is a topic that we study a lot in college, but we've talked about a little bit in math so far. In fact, whenever we do set notation, like when we have a given ordered pair, like this one or maybe that one, I'm actually creating a set of two elements. This one is one element and this is another element. So a set is any collection of elements. I know you guys hate it when I move stuff like that, so sorry, but get used to it. So a set, any collection of elements. So this could be a set, maybe a collection of the numbers 1, 3, 5, and 8. You can see not a lot. Here's another set, that's the empty set. Here's a set of the real numbers, set of the integers. Sets can be done with with braces like that, and just start listing elements. They can be rules. It can be all x, such that x is greater than or equal to -5, and x is an element of the rational numbers. So all the rational numbers greater. That we can create any set that we want. We can make a rule by it. But the interesting thing about sets is that in sort of this kind of overlapping schema, we talk a lot about subsets. One of the things that we said once is that the natural numbers is a subset of the whole numbers, because all natural numbers are whole numbers. So let's give a formal definition for what a subset is. In a subset, B is a subset of A if every element in B, meaning every part of that set, every piece of that set, everything that's in that set, every element of B is also in A. And I'm going to put the notation below. This is kind of the math speak of this. We say B is a subset of A if, when X is an element of B, that means that X is also an element of A. So that just kind of defines what a subset. And there's two consequences of this that are ones that will apply to us. First of all, every subset is its own subset. Every set is its own subset. So let's kind of put a little note there. Every set is its own subset, which means that A is a subset of itself. And that makes sense. If you're an element of A, then you're also an element of A. But this next one kind of doesn't to some people. It's just one we do by convention. And that is that the empty set is a subset of every set. So I can notate that by saying the empty set is a subset of A as well. So this is the general generic definition of that. And if I go through and give some examples of this, here's one. For the 3-digit set 2, 4, and 6, I want to find all of the possible subsets. Well, I could start with the 1-digit subsets. And that would be the set 2. It would be the set 4. And it would be the set 6. Then I could do the 2-digit subsets. 2, 4. 2, 6, and 4, 6. And then I could do the 3-digit ones. 2, 4, 6, which is the set itself. Now I'm missing one. I'm missing the empty set, and I could put that over here. And I sort of love this little, it forms a nice little, okay, that's a terrible shape, but it forms a nice little symmetrical shape because there is symmetry about the number of sets. Those are all of the possible subsets. The possible 2-digit subsets would just be to relist the ones in the middle there, 2, 4, 2, 6, and 4, 6. We talk about set theory because in set theory, the order that you list them strictly doesn't matter. 2, 4 is the same set as 4, 2. If I just list them differently, it's the same set. All that matters is that they're present. So here's an example. If you're on a scavenger hunt, and there are 20 possible items to attain, but you only need to get 5. How many ways can you return with 5 different items? And we assume the order you obtain them doesn't matter. So let's start with saying the order did matter. So if there are 20 of them, you might think, well, that's 20 pick 5. Because if I have 20 pick 5, really that's the same thing as 20 factorial over 20 minus 5 factorial, which is just 20 for the first possible item, and 19 for the second, and 18 for the third, and 17 for the fourth, and 16 for the fifth. And I have 5 items. Well, that might be true, but that actually greatly overestimates how many different possibilities we can have, because this assumes there's an order to them. What I really want to do is I want to say, well, let's do the same 20 times 19 times 18 times 17 times 16, and do what we did back in the previous lesson. Whenever we divided out the number of repeats in some of those words, if I go back, we're actually going to have some repeats here. I have 5 elements whose order doesn't matter, and I can shuffle them around. So just like in your homework, I'm going to flip over to the homework here and look up. Just want to look at one example, a word that pops up all the time, just like in Mississippi. Whenever we talk about Mississippi and you divide out the 4 factorial for the S's and the 4 factorial for the I's and the 2 factorial for the P's, because those could shuffle around in many different ways, we are going to divide out the 5 factorial for the possible ways that these 5, once you pick one, could shuffle around. So basically, one of the things my teacher in 7th grade, the one I was referring to before, Mrs. Hindersman, taught me is that we actually line up 5 times 4 times 3 times 2 times 1, and the combination lines up that way. And we'll hit a little bit more of this here in a second. Now, granted, for multiplying this out, let me pause while we do that. It's going to be a little tough. There's ways that you can kind of cut this a little bit. I can try to cross out the 5 times the... Let's see, 5 times 4 is 20, so that gets rid of the 20. But I'm just left with cutting out a 6 out of maybe the 18. So still not that pretty, but ends up being 15,504, which is much, much different than what the original one was, which was 1,860,480. So when your order doesn't matter, the number of possibilities cuts down significantly. And this is called a combination. In a combination, I can define that as the number of possibilities when order doesn't matter. Order, I could also say rank. If you talk about places or finishing places, when order or rank doesn't matter. There's a very simple game that I can talk about with this, and that's poker. When I was younger, my grandfather and I would play 5-card draw, where he would just give me 5 cards, and then he would have 5 cards. And if you didn't like some of your cards, you could trade them out for new ones, and then you try to bet and guess what everyone else had. Well, that was kind of boring after a while, because they really didn't know much. And so now the popular game for about the last 10 years has been a game called Texas Hold'em, where not only do you get 2 cards, and then you see different cards that are common to everybody, and you have community cards that everyone has, and your opponent also has 2 cards. But once you have these cards flipped, and you can kind of see what they have, you get more cards. You have a couple more community cards. You get another card called the turn, which once you see, then everyone bets again, and then you get a final card called the river, that once you see and everyone bets again, and the order that they appear changes the outcome of the game. Because if these were flipped in different order, you might bet differently. So it's a different that's a different permutation. But the game, the original 5-card game, was a combination, because you get all 5 at once. And that's kind of what a combination's like. So many of you are like, all right, let's kind of get going on this. Well, if I wanted to figure out whether something was a permutation or combination, I just look at order. And I figure out, does order matter? So 4 books in a row on a shelf, that would be a permutation because it's changed depending on what the order of the books are. A team of 6 players from 12 players. I don't care who the 6 players are in, what order they're in. I just want to see who the 6 players are. That's a combination. 6 CDs from a group of 20. Just pick 6, or it doesn't matter. I'm actually going to say choose 6 because that starts with a C, and that's a combination. 10 people in line to buy tickets, that could be very different. That could be a permutation because maybe they're going to run out of tickets before all 10 get to the counter. So let's do an example of a combination. If you have Charles has 4 coins in his pocket and pulls out 3 at a time. So we have 4 coins pulling out 3 at a time, and they're different coins. Notice how they're all different coins, so that's going to kind of affect things too. How many different amounts can you get? I'm not asking what the amounts are, I'm just asking how many different ones can we get. So what I can basically do is say, alright, if this was a permutation, that would be for pick 3. But I do want to divide out the possible ways that those 3 could interchange with each other. And so 4 pick 3 is 4 times 3 times 2 over, and then 3 factorial, 3 times 2 times 1, and that's 4 different amounts that we could get. And that should make sense. I could do penny, nickel, dime. I could do penny, nickel, quarter. I could do penny, dime, quarter, or nickel, dime, quarter. And those are the only 4 possibilities that you can get if you list them by brute force. So then we finally end up with this symbol, N choose R. And I tend to say the word choose as opposed to pick because choose starts with a C. So a couple ways to see how this works. The best way is that, or the very first way I ever learned was N choose R is the same as N pick R over R pick R. Well, that's the same thing as N pick R over R factorial. And that makes sense to me because the R factorial just accounts for the repeats that occur when order doesn't matter. From a straight definition of what N pick R is, remember N pick R was N factorial over N minus R factorial. And now we're just multiplying by another R factorial in the denominator. But typically this is the one I go with whenever I'm writing these out or doing these by hand. And I'll show you what I mean by that. So number 8, how many combinations of letters of the word Excalibur? I've been watching The Sword and the Stone, so King Arthur type imagery is in my head. Taking the letters 3 at a time. Well, how many letters are there in Excalibur? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 letters. So I have 9 letters, and this is almost like Scrabble. I'm just going to choose 3 of them. So 9 choose 3. And I can say that's the same thing as 9 pick 3 over 3 factorial, which is 9 times 8 times 7 over 3 times 2 times 1. So do some canceling, and I get 12 times 7, or 84 possibilities. So pretty easy example to start off with. Move on to the next one. In how many ways can a student select 6 courses from 7 electives and 5 core courses? So we're back to scheduling problems. Now this one's a little bit different. And this is where we start to get a little challenging with this. 6 total courses from 7 electives and 5 core courses. And what I want to do is I want to pick or choose 3 from each of them. So these almost become separate problems in a sense. 3 from the 7 electives and 3 from the 5 core courses. So we sort of start to ignore the 6 courses now. We just say, well, let's just pick or choose 3 from each. This is going to lead me to a 7 choose 3. But this is going to lead me to a 5 choose 3. And the question then becomes, do we add them or do we multiply them? And that's a question of if they are truly mutually exclusive. Mutually exclusive means cannot occur at the same time. So are they mutually exclusive? Can you choose 3 courses from the electives and 3 courses from the core courses at the same time? And the answer to that is yes, you can do them at the same time. These are not mutually exclusive. Just put a better not in front of there. They're not mutually exclusive, so we're going to multiply instead of add, because for each possible selection that we make with the electives, we have that many selections with the core courses. In other words, if I pick one outcome here, then I'm going to have many possible outcomes for the other one. But if I pick another outcome, I'm going to have that many possible outcomes for the other one as well. That's a multiply effect. I should move this out of the way. Sorry. So with 7 choose 3, that's the same as 7 pick 3 over 3 factorial. I'm just going to write this a couple more times. And then we also have 5 pick 3 over 3 factorial. And that's really 7 times 6 times 5 over 3 times 2 times 1 times 5 times 4 times 3 over 3 times 2 times 1. Do some canceling. You get 35 times, and that would be 10, or 350 different, we could say 300 different courses, or selections. We'll just say selections. Okay, number 10, how many ways can a basketball team having 5 players be chosen from 6 seniors and 4 juniors? And here's the key here. This is why I like this problem. Great job, Mrs. Manton. If all are equally eligible. If all are equally eligible, we don't care that they're seniors and juniors. They're just 10 people. So I'm going to do 10, choose 5. Now I'm going to do this by hand, but let's open your calculator up and show you again where this is. If I go to the calculator and add a calculator, or go to the scratch pad, hit menu, probability, and combinations, and I'm just going to hit 10, 5 for 10, choose 5. 252. Not a huge number, something I should be able to do by hand. So that was 10 pick 5 over 5 factorial, which is 10 times 8 times 10 times 9 times 8 times 7 times 6 over 5 times 4 times 3 times 2 times 1. Why do I write it like that? There's just some things that you do when you're very young. This was 7th grade, Carmel Junior High School, and she had us line them up vertically so that they were all on top of each other, and that was always the way I remembered how to do this. I'm not saying that's the way you have to do this, but it works for me. That cancels the 6. Let's see, 5 cancels the 10, 4 cancels the 8, and so I have 36 times 7, or 18 times 4. I'll just do 36 times 7, and that is 182. Better check my math on the, or 252. See, that's why I'm checking my math. Yeah, 21, 252. Don't want to make mistakes and have you guys sketching me on these. 252 possible teams, we'll say. Now, if the team must have 3 seniors and 2 juniors, now we change the problem like before. 3 seniors out of 6 and 2 juniors out of 4. So this become cases that are not mutually exclusive. They're happening at the same time. One is 6 choose 3, and the other is 4 choose 2. And you can do this with a calculator, or I can do it by hand. 6 times 5 times 4 over 3 times 2 times 1 times 4 times 3 over 2 times 1. And that will give me 20 times 6, or 120. Now we go to cards. A lot of these do card games and card hands, so you might want to kind of refresh your memory about cards. There are 52 cards in a deck. Out of the 52 cards in a deck, there are 4 suits. There are 13 cards in a suit. 4 cards of each kind. So how many 10 card hands having exactly 8 cards can be dealt? Well, if you want exactly 8 hearts, what I need to think is that out of that 10 card hand, what I really want is 8 hearts and then 2 non-hearts. So how many hearts are there in a deck? Well, we just said there's 13 cards in a suit, so there's 13 hearts. And how many are there? Well, 13, how many ways are there to choose 8? 13 choose 8. And then the non-hearts, well, that's the rest of them, so that's 39 of them. 39 non-hearts, and I'm choosing 2 of those. And again, I'm multiplying because these, once again, are not mutually exclusive. They're not mutually exclusive because this is happening at the same time. Now, something neat that you'll see about this kind of way of doing it, if I add the 13 and the 39, I'm going to get the 52 total cards in the deck. And if I add the 8 and the 2, I'm going to get the 10 cards that I want. Just a little way to check yourself. Now, for this, I recommend plugging this in your calculator. So, we're going to go ahead and do 13 choose 8. I'll pause this. Times 39 choose 2. And that gives me a lot of possibilities. 953,667. 953,667. So lots of hands having exactly 8 hearts. How many 9-card hands having exactly 4 diamonds, 3 clubs, and 2 spades? So same idea. How many diamonds are there? Well, there are 13 diamonds, and I want 4 of them. And then there are how many clubs are there? Well, there's also 13 clubs, and I want 3 of those. And then finally, there's 13 spades, and I want 2 of those. So again, let's go back into the calculator and plug this in. And if I type that in, I get 15,950,220. 15,950,220. Probably why we don't play many 9-card games. From a standard deck of cards, how many hands of 5 cards, all from the same suit, can be dealt? Well, this one's a little tricky because if we want them all from the same suit, let's just pick one suit. If it was one suit and I want a card of 5 cards, well, let's pick the one suit. Let's just randomly call it hearts or something. There are 13 hearts, and I'm going to choose 5 of them. And those are a legitimate number of possibilities, and we'll say that's for hearts. But then I'm also going to have 13 choose 5 for the diamonds, and then I'm also going to have it, this is a terrible spade, oh, that's not bad, 13 choose 5 for the spades, and then I'm also going to have it for the clubs, which is kind of like a shamrock for all those of you who couldn't figure out how to draw that on the last test. So basically I'm going to take 13 choose 5 times 4. So let's go ahead and plug that in. You can stay on for this one. 13 comma 5 times 4, and 5148. Finally, out of cards, just a fun one. How many possible different lottery numbers are there? This is for real. 6 different integers between 1 and 50. You can pick any 6 different ones, like the numbers 4, 8, 15, 16, 23, and 42 for all you Lost fans. You'll know what that means. But you can pick 6 of them. So really what I'm saying is between the 50 integers, I'm going to pick 6 different ones, and that's 50 choose 6. So if I go ahead and plug that in, 50 choose 6, you can figure out how many different lottery numbers, or how many different lottery tickets there could possibly be. 15 choose 6. 15,890,700. That's how many possible different lottery tickets you can have. And you can start to think about what this point in the chapter is, which is the probability of winning the lottery.